Welcome to qnawire.
So we calculate the full angular momentum vector about the center of mass of the system. So for that we take the instant as shown here in the diagram with the positive x-axis to the right and positive y-axis upward. So these are along the axle, and the positive z-axis is out of the plane of the diagram or out of the plane of the screen. So this is how I will denote the z-axis, and therefore the positive z-axis is towards the viewer. Now we take the upper mass as mass A or MA and the lower mass as mass B. If we assume that the system is rotating counterclockwise when viewed from above along the rod, then the velocity of mass A is in the positive z direction as written here, and the velocity of mass B is in the negative z direction as I wrote over here. Therefore, the speed will be given by omega cross r, and here this will be omega times r, and this will be equal to 4.5 radian per second times r, which is just the magnitude 0.24 here, equal to 1.08 meter per second. So this V is the magnitude of VA and VB. Now let's find the momentum. So we have R to be equal to summation over R cross P. Therefore here this will be R cross PA plus RP cross PB. And since P, the momentum is mass times velocity, and here both the masses have the same value, which is given to be 0.48 kg. Therefore, PA and PB can now be written as, so let's take the mass common from both the expressions. So now we have RA cross VA plus RB cross VB. Now you can use determinant rule to find each of these cross products and add them up and then multiply it by the mass m, which is given to be 0.48 kgs. So doing that, we get the full angular momentum vector to be equal to 0.2177 I cap plus 0.2488 J cap. And the unit is kg meter square per second. The component along the axis is the z component, which has a magnitude of 0.2488 kg meter square per second. So that is the component along the axis. Now for the second part, so the angular momentum vector will precess about the axle, which is the x-axis, which is the y-axis over here. So the tip of the angular momentum vector traces out this dashed circle in the diagram. So L has a fixed angle, makes a fixed angle theta with respect to the axis or with respect to the axis of rotation, which is the y-axis, and this means that tan theta will be equal to tan theta will be equal to the perpendicular component over the base. So in this case, the perpendicular component is the x component of L. So that is equal to Lx, and the base is the y-th component of L. So we write Ly here. So from here we can find theta, which will be equal to tan inverse of the ratio Lx over Ly. So we use these two values in this equation. Make sure you put Lx and Ly. Make sure you put the correct values for Lx and Ly and don't mix them up. So doing that, we get theta to be equal to 41 degree. So this is the angle at which the angular momentum vector L precedes about the axle, which is this rod kind of thing, and which is the y-axis that we took here.